Okay, so welcome everyone to our latest webinar series event, Making Pi from Scratch Rapidly and Memorably. Our presenters are Louis Cavanis and Ken Cavanis. The views expressed by the presenters are not necessarily the views of AMATYC. Commercial products mentioned by the presenters are not endorsed by AMATYC. McGraw-Hill would like to thank for their support for the webinar series. All right, Ken, I will stop sharing now. I'll let you begin sharing yours and let you and your brother introduce yourselves, and I will just fade to the background.
All right, let's see if the share is working. Let's see. I'm not sure if it's working right. Let me just retry.
There we go.
Does that look right?
Looking good to me.
Me too.
Okay. Hi, I'm Ken. I actually teach physics, not math, but I enjoy math. I enjoy figuring things out, looking at patterns. And to begin this process, I was just brainstorming, helping my brother with an idea that interested him, but I got sucked into it and it became a partnership, a research project together.
Hi, and I'm Louis, teaching math students in their first 2 years of college, specializing in helping struggling ones acquire basic math skills. Hence, my natural interest is in extending basic fraction stuff to the max. My brother has been my math partner for some time. We already have our next 4th joint project well underway. We will examine several iterative methods for generating fractions to represent pi better and better. After introducing various theorems, we will state our iterating brackets method, which will extend to all irrationals and will work for rational targets too. We will also find some easily remembered approximations, which is where my interest started. To save time, we will only state theorems here, but provide proofs in a separate section at the end for those who want to check us on all of this. Pi is fascinating, right? That is the ratio of the distance around a circle's circumference to across its diameter. We all were introduced early to 22/7 and 3.14. One month at university, the math club's guest lecturer shared a brilliant and memorable way to remember a good approximation to pi. On a classroom board, from lower left to upper right, he wrote the odd digits twice, 1, 1, 3, 3, 5, 5. He then drew a backslash between the threes, and eureka, 355 over 113, an engineering quality pi approximation, good for 7 digits. In passing, it seems we can thank Archimedes for 22/7 and the Chinese for 355 over 113. Well, 4 years ago, and that's to the month, September, I asked Ken, could we top 355 over 113? By now, we've generated many, many fractional approximations to pi. The one on the screen has some features that make it easy for me to remember. 1, 65, 70, another 70, another 65, all written over 5 plus 2 equals 7, 4 plus 6 minus 1 equals 9, and another 7. But even our best efforts leave quite a memory load. In fact, McLuhan issues this dire warning: all rational approximations of pi are useless. Sounds like a challenge to me. Others report similar results, though. Especially prominent are Apostel, Maxakian, Wisner, and Herzinger. Although we begin simply enough, ultimately we need to incorporate everything from vector addition, weighted medians, mathematical induction, and something called supplementary angles. Along the way, we learn some things, and if you try research leading to publication, you may too. Your paper may end up looking pretty, but it never starts out that way. You will experience frustration facing virtual roadblocks for extended times. Expect these to be followed by the amazing high of breakthroughs. Such patterns can repeat multiple times as you grow the paper. Ken, did you feel energized upon discovering a way forward past our roadblocks?
I certainly did. Roadblocks are funny things. You may push through, you may reach a successful conclusion by working hard, but sometimes it's better just to put it on hold, let the subconscious mind work at it for a while. In either case, when we overcome that problem and we see our way through, it's an amazing high. It is a eureka moment.
I found this true. Working with a colleague helps you through hard times, gives you perspective, and you can learn to view the developing results through the eyes of the reader. A collaborative paper is an ideal way to energize your most insightful students. Ken, you have been a huge advocate of involving your students in your research, right?
I think it's one of the best things we can do is to get students started early working on even a small research project, so that they see that it's not just book learning. So when Lewis first began talking to me about this interest in fractions that approximate pi and maybe better and better fractions, easy to remember fractions, my main contribution was to supply him with some fractions to look at. And even at the beginning, though, I found some features really attracted my attention and caught my interest. And when I shared some of these same ideas with my students or colleagues, or even just people that I ran into outside of class, these ideas did catch their interest. So we'll see if it interests you too. For example, we know pi is irrational, so it cannot be a fraction. It cannot be exactly equal to any fraction, n over d. Now, if I take this fraction and increase the numerator, then the whole fraction increases. If I increase the denominator, the fraction has a smaller value. And that suggests a very simple iterative algorithm to approach pi. If n over d is less than pi, we'll increment the numerator. Otherwise, we'll increment the denominator. On the next slide, we'll see some of the early results. Start with 1 over 1. And if you find that this is less than pi, we have the high arrow indicates we're incrementing the numerator, 2 over 1, 3 over 1, 4 over 1. But as soon as we find that it's too big, now we increment the denominator. And you'll see this visualization gives the first few iterations. We get up to 22 over 7 by the end of this, what we've shown here. And there are a lot more high arrows than low arrows. But this algorithm, although it was very easy to code, and you see on the screen now a OneLine Mathematica program that generates this list, but it is limited. Not only does it approach pi very slowly, but it's sporadic. So the accuracy degrades and then approaches again. And we'll notice this also in the table that follows. So in this table, the first column is step number, and then we have n over d, second column. So these are the fractional approximations. And then the decimal version, how many digits are correct, and the error term. And you notice the first 3 in this list, 3 over 1, 6 over 2, 9 over 3, we haven't gotten better at all. In fact, if we had shown you all the steps, we're not showing all the steps here. We're only showing selected steps. If we'd shown you all the steps, the error term gets worse and better and worse and better. We've chosen just to show one fraction for each denominator, but the algorithm, of course, increases the numerator several times for each denominator. This might be easier to see on the next slide.
Well, plotting the sawtooth process makes it easier to see what happens. As n is incrementing vertically, and that's in blue, The graph approaches the red pi slope from below until it marginally overshoots that target, but it slides right far below pi each time d is incremented. That is, vertical approaches are slow and the horizontal losses are big.
So this gives us the impetus, the idea for the second method, which is to only take one fraction for each denominator. Take the one that's the best, the optimal numerator choice for each denominator. And we call this pair for every denominator, take the optimal numerator. We call this pair the pi approximant. So it's the best fraction with that particular denominator to approximate pi. The process is easy. You just take each denominator, multiply by pi, and then round the result to the nearest integer. That will be the closest we can come as a fractional, as a rational approximation to pi. We'll call this sequence the sequence of all pi approximates, and we'll see that on the next slide.
This adaptation of our previous table adds our second attempt. And look 2/3 of the way down, at the yellow arrow, we now get to 22/7 at step 7, 4 times faster. But really, if you look at the number of correct digits column, it grows very, very slowly.
For what we do next, it's helpful to consider the error term. How far is each fractional approximation off? How far away from pi? So we'll define the error as n over d minus pi, where n is that optimal numerator for that particular denominator. Since this rounding process can move the values up to half of an integer, 0.5, that means n minus d pi is bracketed. It's between two error bounds, minus 0.5 up to plus 0.5. And then dividing through by the denominator, we see that this does give an upper bound for the error in each case. It can be no more, in fact, it cannot equal 0.5 divided by d. So that's a maximal bound for the absolute error. As a physicist, when I hear absolute error, I wonder, could we also do a relative error? In this case, comparing the error, the actual error for any case, to the maximal amount that it could be up to 0.5 over d. That ratio will also be useful as a way to say how good our approximation is. The next figure shows the errors, the absolute errors for the first 45 denominators, and then we'll think about relative errors after that. So I like this graph. You can see the dots. If any dots that are close to the horizontal axis are good approximations to pi. If it gets farther away, then it's not so good. We also see a gray bounding envelope on the top and the bottom. That is the plus or minus 0.5 over d bounding envelope. So the points that are close to the bounding envelope are particularly bad, I would say. And the ones that are close to the horizontal axis are particularly good. But I'm disturbed by this representation because, as we see, the first dot that's a pretty good pi approximate is 22/7. And then we go down a little farther and see 44/14 is classified as the same quality of approximation. And I don't like that because it's not reduced to lowest terms. It's the same error. In some sense, 44/14 should not look as good.
So if we instead compare their relative errors, and this is in figure 5, 22/7 and 44/14 are not equally good. You can see that 44/14 is a little farther away from the optimal horizontal line. Since 44/14 is larger when compared to the error limit 0.5 over d. We notice that the first real improvement after 22/7 is over on the right-hand side at 355 over 113.
So this gave the reason for our third method, which is round to find the best pi approximate, but only save the ones that are better, the ones that are better than what we found so far. There's a few lines of Mathematica code there on the screen. We start with 3/1 as the best approximation for the denominator 1, and then we will only append to our list pi approximates that are better, that are closer to pi than the previous ones in our list. This is what we call the gold list, the gold standard. And this table shows the first 17 items in the gold list. So the first column shows steps, and the second column shows these increasingly good, better and better pi approximates. And this table really shows the whole meat of the presentation today. It's not where we end up, but it does give you the insight, the reason for why this caught our interest. If you spend just a moment looking at the table, you'll see it too. I've shared this with 100 different students, and it blows them out of the water. So let's see if everyone can catch what's going on. Column 2 are these recent good approximates. So 3/1, and the next best one, the next one that's better than that as we go down is 13/4, 16/5, 19/6. Step 5, we got up to 22/7. And yes, the number of correct digits is improving as we go down, never backs up, and the error terms are decreasing, at least in absolute value as we go down. But I did not ask the question that really opened this up. Lewis asked this question, and it never occurred to me. So if we look at these pi approximates, we see the numerators are growing, the denominators are growing, but he asked how much. And you look at the first few, 13/4 and then 16/5. It looks like the numerators are growing by 3. The denominators are growing by 1. A little later down, 179/57, 201/64. Now it looks like the numerators are growing by 22 and the denominators by 7. And we've added a column, next to last column, which is the change in numerator and the change in denominator. And all of a sudden, the ground falls out from under our feet. Why should the change in numerator and the change in denominator look so familiar? We have 3, a change of numerator of 3 and a change of denominator of 1. Well, 3/1 is a pi approximate. And then later, 22/7 is a pi approximate. This is just earth-shaking. When we first saw this, we had no idea why it should be this way. And it sent a shiver up and down my spine. I could not understand. In fact, I tried to talk Lewis out of it. This isn't real. Something is wrong here. These fractions came about from a very mechanical process, throwing away the fractions that don't improve, don't get closer to pi, and the differences in numerators can't mean anything. But they do. Lewis, tell us about it.
Let's look more closely. Consider any point in this table marked by a solid horizontal line. For instance, between steps 5 and 6. In the N/D column, you notice above the horizontal line, we have 22/7, and below we have 179/57. And they're both members of the gold list. That's why they're in this column. But if we add their numerators and add their denominators, a process we were taught not to do with fractions, and I have to tell my basic students this over and over again, we get an even better pi approximate, 201/64. In fact, repeated, quotes, funky addition of 22/7 continues to yield the better and better pi approximates shown in steps 7 through 14, until we finally reach a far better one, 355 over 113. This unexplained oddity leads us to a real breakthrough by asking these questions. What Ken mentioned, why do the highlighted fractions in the n over d column reappear in the change in n over change in d column? In fact, following the dotted and solid arrows, how does adding 3 over 1 3 times to 13 over 4 result in 22 over 7? And we could ask the same question about the next grouping. Here we're adding 22 over 7 8 times to 179 over 57 and arriving at 355 over 113. What's going on here? Our discovery resulted from noticing these step differences. This anomaly disturbingly resembles fraction quotes addition by adding numerators and adding denominators, a common error of struggling basic students. Yet these very questions lead to an extended accelerated method for generating all pi approximates. So we will be forming medians. The operation of adding numerators and adding denominators separately is called officially the median, disparagingly, the freshman sum, and alternatively, the fairy mean. So our definition is the median of progenitor fractions a over b and c over d is defined as a over b circled plus c over d equals the quantity a over a plus c all over b plus d.
So we've defined something, and the next step would be to make use of it. It's not really hard to see that the median of any two progenitor fractions lies strictly between those progenitors. For example, if you take 1/3 and 1/2, form the median, you'll have 2 over 5. And 2/5 is between 1/3 and 1/2. We proved this rigorously, mathematical proof. And then we found that other people had already done so before us. So the moral of that story is don't skimp on your literature search when you are working on a paper. You might be reinventing the wheel. Now, next question would be, if we take two pi approximates and form their median, will the child, the median, also be a pi approximate? So when is this property of being an approximate passed on to the median child? Theorem 1 gives the answer. When pi approximates a over b and c over d are on opposite sides of pi, then their median will also be a pi approximate. Again, this proof is not too hard to walk through. You can check it out after the webinar in the slides that are in the supplementary section at the end. And an interesting footnote is, even if the two progenitors are not on opposite sides of pi, it can still be shown that one of the three fractions at the bottom of the screen is a pi approximate. So either the median itself, or just add or subtract 1 from the numerator, one of those three fractions will be a median. Will be a pi approximate.
In figure 6, upper right, we're going to contrast or compare the median in vector form with it in slope form. Geometry here allows us to visualize what algebra has proven. The median of two opposite-sided pi approximates is also a pi approximate, and this is an important feature. It's closer to pi than at least one of its progenitors was. So here we have two progenitor vectors, v and w, in green, and their median in blue, of course, using the parallelogram feature. Notice that it lies between them, but notice that it is closer to the red pi slope dotted line than the vector w was. And this is always true. So we can get closer and closer to pi this way. And it gets better. If pi is bracketed, by 2 fractions, we can jump directly to a much smaller interval that also brackets pi more closely. In other words, by using medians of pi approximates, we enclose pi tightly in ever-shrinking intervals.
So now we have a process that will give us closer and closer bracketing of pi. This is our fourth method. We define a bracket. So this will be 2 fractions on opposite sides of pi. We'll take, in fact, any positive real number target r is bracketed by a set of non-negative fractions. We'll use curly brackets. We choose, as a matter of just convention, to list the fraction with the smaller denominator first. So a over b comma c over d implies that b is the smaller denominator. We don't have these in ascending numerical order, but in early order. So b, a smaller denominator, would be earlier in our list. We'll call that the earlier fraction, and the second fraction in the bracket will be called the later fraction. Of course, the bracket corresponds to an interval on the real number line, and the length of the interval is just the absolute value of the difference between the fractions.
For irrational targets, all intervals are open. And in the appendix, we will consider the case in which the rational target equals the later fraction. So now we can reconstruct our goal list simply by repeatedly constructing medians, which motivates our next step.
So if we add 3 over 1, and we should say add in quotes, add 3 over 1 to 13 over 4 3 times, we'll get better and better pi approximates. First 16 over 5, 19 over 6, and finally 22 over 7. So in 3 steps, we accomplished the same thing that previously took us 28 steps in the first method and 7 with our second, and still took 5 steps with the third. But in the next breakthrough, we'll see how using repeated medians, we can do this all in 1 step. And Lewis will start us in that process.
First, we generalize the mediant concept to weighted mediant, allowing multiple additions of the same earlier fraction, a over b only. Here we use the circle dot symbol to indicate these multiple medians. By the way, this weighting is like the process an instructor routinely uses in calculating grades when the different assignments or quizzes are assigned different weights. Second, we extend the median inequality to the weighted medians. If v is less than w, their median's order actually depends on the order of the fractions a over b and c over d.
The weighted medians also lie between the progenitors. And as the weighting index changes, as the index increases, medians move from the later fraction towards the earlier fraction. So they will move from c over d towards a over b. For example, if you took the initial bracket, 3 over 1, 13 over 4, we'll get the weighted median sequence, 13 over 4, 16 over 5, 19 over 6, 22 over 7. These are all in the gold list. And because each one of them is on the same side of pi as 13 over 4, they will monotonically approach pi from that side. This is much easier to see on a number line.
Well, in figure 7, we have the previous bracket overreaching in blue and the next bracket in purple. We progress right to left, starting at median by median, starting with the previous bracket, 13 over 4 on the right and 3 over 1 on the left. And we're actually progressing to the next bracket, which is 22 over 7 and 25 over 8. And we travel from the later progenitor, 13 over 4, toward the earlier one, 3 over 1. In a nutshell, this is actually a summary of our whole result. our process will skip 4 times to the 20/5 median past pi, and it remembers the 22/7 median just before pi, and it calculates, it will tell us how many medians we should skip, and it calculates of the two that 22/7 is closer to pi.
So each bracket will give us the next much smaller bracket. The next weighted median sequence, starting with the bracket 22/7 and 25/8, will produce the following bracket 333/106, comma 355/113, which is a familiar one. In order to really see the progress here, as the index goes the weighting index goes from 0, 1, 2, 3, 4, we better zoom in. Those first weighted medians are not closer to pi than pi approximates that we already have in the gold list. So let's zoom in on the new ones. Here we've zoomed in, and the 6th weighted median is still not as good as previous things on the gold list, but starting with the 7th, these are all better. So the 7th through 14th, actually the 7th through 15th medians are all better than anything we've seen previously. So we need to find a way to know when to start using the weighted medians. And this is where the explementary angles come in. When one of the weighted medians is greater than or has passed the 2 pi minus 22/7, so that is the explementary angle for 22/7, then those start being in the gold list. Who knew that explementary angles could have anything to do with this? Of course, the explementary is similar to the supplementary, complementary, just using 2 pi. Tell us about the crossover now.
Yes, our next theorem. For any bracket A/B, comma C/D, we can now calculate where the weighted median sequence will cross over. Use the crossover kth median with its crossover index k to equal the ceiling of kappa. And kappa was a great breakthrough for us, where kappa is defined a couple ways, but particularly the denominator's ratio D/B multiplied by the quantity pi minus C/D over A/B minus pi. Now I find this interesting. The numerator and denominator in parentheses tell us the distances from pi for C/D and A/B respectively. Their ratio then will give the irrational number of median steps needed once D/B scales that by the ratios of the denominators. Of course, k converts kappa to the necessary integer steps. Going forward, we will take as our next bracket the weighted medians on either side of pi, the k minus first and the kth medians.
So we start with a bracket, we go to the k minus first and kth median, and now we'll have the next step in the process. The proof that this works is again in the supplementary material. We won't look at it right now, but we are able to predict how many times to repeat the median addition directly using the kappa or the k. One remark, in Theorem 4, we will get around to addressing whether to include that kth median in the goal list or not. It will be part of the new bracket, but it's not immediately clear if the kth median should be in the gold list. That was the only missing piece at this point in reconstructing the gold list quickly. So that we'll cover in Theorem 4.
As a corollary, called the gold median corollary, any weighted medians with indices greater than or equal to j, as defined in equation 5, will be in the gold list up until the k minus first mediant. Equation 5 states that J is defined as the maximum of 1 or the ceiling of eta, where eta, sort of like we did with kappa, is defined as 1/2 the quantity of kappa minus d over b.
So this tells us where to start counting, putting these new entries into the gold list, and we almost know where to stop. We will cover that in a moment. So as I mentioned, this proof uses the concept of complementary angles, which is a natural extension of the complementary or supplementary angle idea, but subtracting from 2 pi rather than subtracting from pi over 2 or pi. Another just quick remark, if j equals 0, we already have that weighted median. That's one of our bracket elements in the list. So the 0th median we would not add again to the list. But all further medians after j equals 0 up to k minus 1 will be closer to pi than anything we've seen previously and automatically go into the gold list. And we could go back to one of the figures and see this, that the 7th median is the first one that goes into the gold list as the first one whose distance from pi is less than the distance between 22/7 and pi.
Here we're going to look again at figure 9, and we can see clearly that j equals 7. It's just barely, but it is past that 2 pi minus 22/7 benchmark. So all further medians up to and including the 14th are monotonically approaching pi.
So just to back up for 1 second, the point is to find all fractions that approximate pi better and better. And this method is the quickest way to do so. We just put in all of these weighted medians at once into the gold list. So to summarize, the sequence of ith medians, of weighted medians, starting with j, that's our gold index, going up through k minus 1, where k is defined in terms of this kappa. These are all going to be in the gold list. The kth median itself may or may not. That piece is still outstanding, still to be considered. And we always can make a new bracket. If we start with a bracket a over b comma c over d, take the k minus first and the kth median, weighted medians of those fractions, and we will have a better bracket. So we can iterate this process indefinitely, creating better and better brackets.
So our 5th and final method is almost complete. From each set of fraction parts, A, B, C, and D, we generate first K, and then the next set of numerators and denominators, and shown in this definition 4. The next A over B is defined as the K minus first median, the earlier median, and the next C over D is defined as the kth median.
That is an iterative process. So theorem 3, again, we'll postpone the actual proof. It's in the supplementary material. But this, we have 3 parts which we have proven that this iterative process will generate a new and better bracket for pi. Also, the endpoints of the brackets are reversed every single iteration. That's an interesting thing. Reverses the order of the endpoints, and the separation, the length of the interval that corresponds to this bracket is reduced every time. Now, one feature we noticed is if this additional stipulation, additional criterion is met, that the absolute value of AD minus BC is equal to 1. We recognize that as looking like determinants of 2 by 2 matrices. Well, if that is met, then that property will be inherited by the next bracket in each iteration. And the bracket length is equal to 1 over an integer, b times d, and this length is always less than half of the previous interval. So we can specify how fast the length is decreasing.
So the first claim, this new method generates a new smaller bracket of pi approximates. Claim 2, the new bracket is in reversed order. And Ken?
Claim 3, the new bracket has this reduced length. And with the additional criterion, the factor by which we reduce the length is at least 2. Fun fact, this proof required mathematical induction, and some of us feel that that makes any mathematical paper feel a lot more solid. Now, in the case that a times d minus b times c is equal to either plus or minus 1, the interval length, this property will be inherited by each child bracket. And so we found even if we don't start with the property, it turns out to gain that property, and then from then on it will be inherited. So that was an interesting feature too.
The minimum bracket length, which is marginally greater than 2, occurs when k equals 1. At the other extreme, if k is much, much greater than 1 and b is approximately equal to d, we get a much different ratio. The ratio of the current bracket length to the next bracket length is going to be of order k squared. So iterative brackets provide a faster way to approach pi and magically replicate the goal list. But next we need a definitive way to choose which bracket element to include in our track fractions, either the early or later one. In practice, we can find each subsequent kappa directly from its predecessor as given in equation 9. This has very interesting results and ties in nicely with the method of constructing continued fractions. See that in the appendix. From our research data, we're looking at figure 11 now. I noticed that this ratio shown in figure 11 correctly predicts the next kappa sub m plus 1. That is the ratio of kappa sub m's difference from its ceiling on the right to its difference from its floor on the left. Naturally, the signs change because kappa sub m lies between the two. So I was not at all surprised when Ken rearranged equation 9 in its current form. In our partnership, I see these empirical relationships while Ken insists on the theoretical proofs. Our final unexpected breakthrough reveals that kappa itself contains enough information to know which bracket element is closest to pi, and therefore to decide whether to add the kth median to the gold list or not. Here are two equivalent tests in equations 10 and 11 for consecutive generations of kappa. Let's focus on equation 10. It states that for the m plus first step, test whether kappa is less than d over b. I wonder, why does the ratio of denominators keep showing up earlier in the kappa and eta definitions as a factor and a minuend, respectively, and now as a test? Is it a curse that I must always know why? Although curiosity drives us, research is never ending. So an important principle is know when enough is enough and when to stop and publish. True, Ken?
Well, changes to the PowerPoint this week were probably, we should have left things alone. We had the structure in place. Anyway, we now have, on this journey to find better and better pi approximates, we have fast ways to add in large numbers of new pi approximates in one swell foop. So the express lane is just to take the better and better brackets. So the iterative bracket method. The scenic route would be to fill in the gold list as we go. In the express lane, you generate new brackets, and each one we get a new kappa, a new k. And then theorem 4 will tell us which of those two in the bracket, in the new bracket, is the best approximate so far. The lower limit of convergence towards pi is a factor of 2 per iteration, but in practice we found that the average was closer to a factor of 10. So each iteration gave us 1 extra digit of precision in base 10. On the scenic route, besides calculating the brackets, we can put in all elements that will be in the goal list. And by looking at theorem 4, we're able to decide that last piece of the puzzle, whether the kth weighted median should be included also. So now table 6 gives the results for our 5th method, demonstrating the first 15 steps of the iterative bracket median choice method. We'll skip the cases where k was equal to 1 because that means k minus 1 was equal to 0 and one of the bracketed elements didn't change. Other than that, we're showing in column 1 all the steps, the step number, and the second column tells me which element in the gold list it is. So you see after step 5, we've already constructed 162 elements of the gold list. After 15 steps, we've already got 180 elements in the goal list. And the third column shows us one of the bracket elements, the one that's closer to pi in each case. So in 15 iterations, we have generated 17 correct digits. We have a pi approximate that's correct to 17 digits, and we filled in 180 elements of the gold list. So that is, in 15 steps, doing what our best previous method took 180 steps. And the speed increase is staggering. When I ran this on a Core i5 2 gigahertz computer, comparing the previous method to this 5th method, the iterative bracket method, I saw just an amazing enhancement. To generate 163 approximates of the goal list with the previous method took 8, almost 9 seconds of CPU time. By contrast, the new method took less than 1 millisecond, 0.836 milliseconds in 5 iterations to reach the same point. And the iterative bracket method we have extended far, far beyond any other way of calculating the gold list. In 80 steps, 80 iterations, we have a rational approximation to pi, shown here on your screen, which is 40 digits of numerator and 40 digits of denominator, and is accurate to 80 digits of pi. That only took a 1/32 of a second. And the previous methods would not get there in any realistic time.
Table 7 coming up lists estimates with mnemonic potential, which was part of my interest. This now completes our journey to find rapidly more accurate and memorable rational approximations to irrational pi. But still, we must memorize 40 numerator and plus 40 denominator digits to get 80 digits of pi. So McLuhan had a point when he blogged, all rational approximations of pi are useless. Here's table 7. We're listing a few cases that look mnemonically interesting to me. These were mined from the gold list once it was generated far enough. Look at particularly the last line, 33 digits of pi. Notice how odd it is that you have repeated digits of 6, 4, 5, 8 in the numerator. So it's possible that a person could memorize that. But there's no reason to stop at pi. This same iterative brackets algorithm can be extended to all irrationals. Here are a few selected examples. Some irrational, like e to the pi, power, etc. Some rational, either repeating or terminating.
The method was not limited to pi. And here's what happens if we try to apply this method to a rational target. So the gold list generated with a rational target, this is the target that was the last entry in the previous table, table 7. It is the number of weeks in the calendar year using the leap year definition of the Gregorian calendar. So the first approximate to this target is 52/1. There are approximately 52 weeks in a year. And the next one is 157/3. And you see these are getting closer and closer to the rational target now. And the very last one is the exact fraction. So the method works, but it will end, it will terminate at the desired fraction. That's the only difference between applying the iterative bracket method to a rational target compared to applying it to some irrational number. I found that extremely interesting.
In the supplementary material in the appendix at the end, you can find proofs and derivations, including the treatment of this rational target case. We mentioned advantages and comparisons with continued fractions, Greek ladders, and logarithmic approximations. And there you'll find the mathematical code for the iterative brackets method, and then our references. In memoriam, Ken and I wish to recognize Professors Tom M. Apostol of Caltech and Robert J. Wisner of New Mexico University for their extensive and significant contributions to mathematics during their lifetimes, and for their obvious love of mathematics, inspiring listeners and readers alike. Several of the references in this papers are due to them. We relate to the phrase, standing on the shoulders of giants. Thank you.
So we've switched back now so that we can see the chat, and if anybody had any extra questions or comments, we'll be able to respond in the time that remains. So thank you for the kind words. That's pretty clever and simple. Isn't it surprising how often the pattern will then lead us to something? Patterns always mean something, it seems to me. But what it means takes us some work to figure it out. And then afterwards we say, oh, it was obvious. It's funny how often this happens. So any other questions or comments people have, feel free to add to the chat there. I'll just say one more thing, that I've shared this with at least 100 students here at our university, and maybe people that have no interest in math at all, but their interest is caught by this surprising feature, a pattern that doesn't at first seem to have any explanation. And in physics, I would say any pattern means something. There's a very, very high probability that it means something. And so showing students a pattern is the best way to entice them to think.
Thank you all.
I think, Pat, your microphone is still muted.
That might have helped. I've been talking for the last couple of minutes. Thank you, Ken.
Sorry.
Looks like they were giving you thank yous anyway. Yeah, we're, if you're not a member, consider being a member. We are on Facebook. We have some upcoming conferences, webinars, traveling workshops, plenty of ways for professional development. There is a position in AMATYC leadership for a professional development coordinator. So if professional development is something that you're very interested in, you might want to consider that. We will save this, we'll stop the recording here in a moment, and we will upload this to YouTube. Ken and Lewis will share the full PowerPoint along with some materials. Is that correct?
Yes.
Yes.
Okay. And as soon as we can get that sent into the website coordinator, we'll get that posted and we'll notify everybody when it's up. Also, we have an evaluation here at the end. You can either copy and paste or type in the link, or if you have a QR reader, you can go straight to the survey evaluation from the QR code. We'll leave this up for another couple minutes. Thank you again for attending. We'll leave the survey open for a few days to give everybody a chance to go in there and do it. Ken, Lewis, any final comments you want to make?
Just thank you for agreeing to hear our story.
I enjoyed it. It was quite interesting. I'd have to spend some more time with it to get to the level that you were talking at the end. I kind of a little overload, but it was quite interesting. Thank you for wanting to share it with us.
Thank you. And keep looking at those patterns.
All right.
Absolutely.
Any other questions or comments from the chat?
Eat a donut on us today. It's a circle.
They will begin eating pie. Yeah.
Good idea. Okay, well, gentlemen, I think I will go ahead and stop the recording. If anyone wants to stay and